consider this marker that's sitting on a ruler between the tabletops. You'll notice we've got a desk table over here, and we've got one of the tabletops there. It's suspended across a ruler or meter stick across the middle, and the marker is sitting on there, just suspended between the two. And so that's a situation we'd like to consider. Taking this to cartoon version, it looks something like this. Well, the first thing we want to do is ask, is the marker moving? And there's a variety of ways we can do this. In class discussion, some students said, well, of course the marker is moving because the Earth is spinning on its axis and it's revolving around the sun. Our solar system is rotating within our galaxy, so of course it's moving. But if we look at it relative to its immediate space, and we define the system just as the marker, its immediate surroundings, and the Earth, we could say that the marker, under those circumstances, has a velocity that equals 0. And then I asked, is it accelerating? Well, based on the previous assumptions that we're only comparing it to its immediate surroundings, its position's not changing, it's remaining at rest, the velocity's not changing, the acceleration must be 0 as well. Next up, I asked, what forces are acting on the marker? Well, instead of talking about what forces are acting on the cap and the ink cartridge on the inside, right? If there's a cartridge on the inside, I guess that would be green ink that's on the inside and all of that. We decided to decide that we're going to use this one dot to act as the center of mass that represents the entire marker. Center of mass. So this red dot represents a whole marker. Well, what is acting on the marker? Students quickly said that gravity is pulling on the marker. I asked which way, they said down. So there's a force of gravity acting on the marker. And what is pulling down on the marker? What is that gravity? Well, if we take a look at the definitions that were shared out, we know that gravity, it always has to be a pull between two objects with mass. In this case, one of the objects is the marker, and the other one happens to be the Earth. So the Earth and the marker are pulling on one another, but in this case, we're only talking about the fact that the marker is being pulled downward by the Earth. What else is acting on the marker? Well, some students said that the ruler or meter stick is. We decided to call it a ruler in this case. And because the marker continues to be at rest, it's sitting at rest, it's not changing its motion, all right? We decided, the kids said that those forces must be balanced. And what is pushing on the marker? Well, it's the meter stick, which in this case is acting like a table or a floor or a surface. And according to our list, a normal force is perpendicular to a surface. So we'd say force normal on the marker by, we're going to use R for ruler. And we need to use a vector up here because forces are vector quantities because direction's important. We want to identify that these are the same length as each other. I can measure them out with my fingers or put the hash marks on them. Now, what would happen if we said that the upward forces were positive and the downward forces were negative? Well, if we had an upward force that was this big and that it happens to be exactly the same size as this downward or negative force, what would happen if we added them together? You know, if the upward force was a positive force something and the downward was a negative force, if we added them all together, if we took the sum of those forces and added them together, the sum of the forces would equal 0. The same size positive force plus the same size negative force, those would equal 0. We're going to abbreviate that using the Greek letter sigma, which stands for sum. Right? That's the Greek letter for S, for the sum or add them all up. And then a capital printed F with a vector for forces. This, we're going to say this as net force, or sum of the forces. Net force. That's crazy, right? In which case is 0. Now, when looking at the naming of this, look at the force of gravity on the marker by the Earth. So I think it's pretty easy that the big F stands for force, and the big G stands for gravity. The big M stands for marker. The big E stands for Earth. But why do we use this? Well, the big F stands for force, and that's all that is. It's telling us that this is a force vector. In this case, we're going to use the word of. Gravity is the type of force that's acted upon. Let's see. Type of force. Scroll this down. The marker is the victim or the feeler of the force, and in this case happens to also be the system. So that third symbol will always represent what is represented by the system. And the last thing is the dealer of the force. In this case, the Earth is pulling on the marker. So in this 4-letter naming system, force of gravity on the marker by the Earth, the first letter is always F for force. The second letter is the kind of force or type of force it is. In this case, it's gravity. The third thing is the feeler or the victim of the force. In this case, it's the marker that's being acted upon. The fourth symbol is the Earth, and it's what's pulling on them. So force of gravity on the marker by the Earth. Up here, if we take a look at this other force naming thing, we've got force. In this case, we don't say of normal, we just say force normal. Force normal on the marker, and it's by the ruler. Force of gravity on the marker by the Earth. So hopefully that helps you better understand both the concept of how to build a basic force diagram, a basic naming system using these 4-letter subscripts, as well as an introduction to net force. Net force again being the net force. In fact, if we were to take the normal force away, if we removed the meter stick, the ruler, what would be left over? It would only be the force of gravity, in which case if you have force of gravity pulling down and there's no force pulling upward, then the force of gravity on the marker by the Earth would also be the net force in this case.